In this example, we're going to do a single factor Anova F test using software. We're going to calculate a side-by-side box plot, and we're going to perform a multiple comparisons procedure for means. The following are recording times in minutes for 3 different artificial intelligences to complete the same task. We want to consider the data to be random and the populations to be normal with an equal variance. So it looks like there's robot 1, robot 2, and robot 3, and for each robot there are 5 time measurements in minutes to complete the task. Is there evidence the average time to complete the task differs between the robots? We're going to use software to obtain a side-by-side box plot, an Anova table, and perform a multiple comparisons procedure. And we want to use this output from the Anova F test with a significance level of 0.01. So we want to perform an F test. So what that means is that we need to state our null and alternative hypotheses. So our null hypothesis for a single factor ANOVA is that mu, so the robot mean for the first robot is equal to the mean of the second robot is equal to the mean of robot number 3. All right, so all the means are equal to each other, and the alternative is that at least one mean or at least 2 means differ. So for us to perform this analysis, we should check some conditions. We need to check whether or not our populations are normal. And we have that information that's been given to us. We need to know that the data is random. And that assumption has also been made for us. And then lastly, we need to know that the variances of each group are equal to each other. So the population variances are assumed to be equal to one another. So these all have to be equal to each other for us to do an ANOVA F test, or they have to be somewhat similar. They have to be somewhat symmetric populations for this to not have a large type 1 error or an increased type 1 error. So we have been given all the conditions, and so we see that all of those have been met. So the next thing we should do is look at this information. Based upon our data, we can't just say, oh, robot 1 is better than robot 2, better than robot 3. We need to do it in software. So let's go ahead and go over to our studio. The first thing we need to do is run the times in. So this is our time vector. This is our response variable. Time is equal to 2.27 for the first robot. It's first observation, second, third, fourth, fifth. For the second robot, it's 2.34 is their first observation, second, third, fourth, fifth, and so on. So we run the time in as its own vector. And then we run in the treatment group, or the different populations or different groups. In this case, those are the different robots. And I'm going to call this vector AI, artificial intelligence. And I'm going to repeat the word robot 1, then 5 times, repeat robot 2 5 times, repeat robot 3 5 times, and I'm going to call this a vector AI. This just defines my treatment groups, and then I'll combine these with the command cbind. I'll say I want my response variable time to stay as it is, and I want AI to be considered a factor variable. And if I run this as my data, and I look at it, I can see that, sure enough, I have a vector of my responses, and that I have 5 1s, 5 2s, and 5 3s. And so that's important to do that so that I can use the commands with the tilde instead of all separately. It's important that we run our data in like that. It's in that structure to be able to do an ANOVA F test. So let's go ahead and check out a box plot of this data. So box plot is time versus artificial intelligence, and we can see that robot 1 is here, robot 2 is here, and robot 3 is here. So just from looking at the side-by-side box plot, we should see that there should be a significant result from our overall F test. Essentially, it looks like all these centers are very different from each other. Robot 3 seems to be the fastest, robot 2 is second fastest, or robot 1 is the second fastest, and robot 2 seems to be the slowest of the group. So these are very separated from each other. It does look like the variability is about the same in each group, and each group is relatively symmetric. So that's good for our conditions for our test. If we want to just look at the mean, the variances, and the sample sizes for each, we can use the command aggregate for time versus the the subjects or the groups, and we can calculate the mean, variance, and sample sizes. We can see that the mean for robot 1 is 2.26, the mean for robot 2 is 2.336 minutes, and robot 3 is 2.178 minutes. And it looks like the variances are all about the same, slightly different, but they're small sample sizes, and so the slight variation isn't going to be a big concern. And we can see that our number of observations in each group is equal, all equal to 5. All right, so the next thing we want to do is we want to set up our single factor Anova F test and get our Anova table. So if we just run this AOV time versus AI command, we can see that we actually just get our sums of squares. We don't get everything that we want. We only get the sums of squares and the degrees of freedom, which is fine. We can still calculate the F test, but it's not as much as we want. So let's call this something. Let's call it mod. And then by running this as mod and taking the summary of mod, we then get an Anova table. So we have to do a little bit of finagling, but this is a good way that we can do this, because when we do multiple comparisons, we can still use that command or that structure mod to calculate the multiple comparisons procedure. All right, so we can see from this, as we should have expected, that we have a pretty small within variability, 0.000433. So that's the mean squared error. That's really small. So that's the within variability. That's going to account for how wide these boxes are down here. And then the between variability is the variability between our centers. And we can see that that is very large for the 3 different robot groups, so it makes really large in comparison. So it makes sense that our overall F test statistic, the ratio between these two, will be very large, which it is. 72.05 is a large F test statistic, and therefore it should result in a very small p-value, which it does. This is 0.000060 zeros and then a 2. So that's a really small p-value. It's very significant, which means that there is convincing evidence that at least 2 of our means differ. So if we look back to our original assumption, we can see that this was our null hypothesis. We're definitely able to reject the null hypothesis at a significance level of 0.01, and we could see that at least the 2 of the means differ. So there's convincing evidence in favor of our alternative hypothesis. Now we want to see which means differ significantly and by how much. So if we go back to our software, we can run the Tukey HSD line. We have our mod, which is the same thing as up here, and the confidence level we want to use is 0.01. So that's the family-wise confidence level. If we were to just run several t-tests, then we would increase the chance of type 1 error, because just by chance we will reject 1 out of 100 tests if we use an alpha level of 0.01. Even if the null hypothesis is true, we're just going to reject by chance. That's the way that it works. So essentially we want to do a simultaneous test, and that's what Tukey HSD does, is it runs all the tests at the same time. And essentially what it does is the individual error rate or the individual significance level is dropped so that the overall confidence level or overall error rate is equal to, and this should actually be 0.99 and not 0.10. So we'll change that to 0.99 as our confidence level. Rerun this. And that makes a little bit more sense. All right, so basically our overall confidence level is 0.99, not 0.01. And we can see that our confidence levels all are now at a family-wise rate at 99%, and then all of these p-values have been adjusted for a 0.01 significance level. So essentially we can compare these to 0.01 and say that they are significant or not. It does look like every single one of them is significant. And so for robot 2 versus robot 1, so this is robot 2 versus robot 1, it looks like robot 2 is 0.076 minutes slower than robot 1 on average on doing the same task, with a confidence interval from 0.029 to 0.1229. And so we can see that this doesn't span 0, so it's definitely going to be significant at that 1% level, but we can also see that from the p-value. It looks like the difference between robot 3 and robot 1, so these two, is negative 0.082, so that means that robot 3 is 0.082 minutes faster than robot 1. And then again, its confidence interval goes from negative 1.28 to negative 0.035. It has a very small p-value as well. So the difference between these two, from the simultaneous test, is still significant. And then the difference between robot 3 and robot 2 is the largest difference, and that is 0.158, which we can see should be the biggest difference if we look between robot 2 and robot 3. It has an average difference of 0.158 minutes. So robot 3 is 0.158 minutes faster than robot 2, with a confidence interval that spans from 0.2049 to 0.111. And so what that means is robot 3 is 0.204 minutes to 0.11 minutes faster than robot 2 when doing the tasks on average. So this is the way we can then see which means actually differ, and we can protect ourselves from making a type 1 error based upon just doing multiple procedures.